I know, yeah, with the hair.
Oh, I went out in the hail like last
Last
night.
night I was out
But-
I went to run about 1:45 to midnight last night.
Did you run on
About 3
Sunday?
kilometers.
Did you on Sunday the flooding?
See if that's
That
what's-
is
That
Some
was
days-
what's it called, like a 2-piece marathon you did running and biking.
Yeah. I'm
also
impressed.
run at night when I get home from the pub if I've forgotten to run that day or I haven't.
When you get back from the pub.
Wait, so broke there and then
Can you imagine why you couldn't have a chips?
To be fair, when I'm hungover, I always go for a run.
Chips is not very good.
But they do
I
argue
eat
on
lots of rice because that's Persians' main, like you eat chips, we eat rice.
it. Chips
So
that
maybe
much.
it's
I love the idea that most people after the flood but will kill you goes
Quick one. Okay.
Anyway, maths, yeah.
What? Oh, what's that?
Why don't you set one of the questions, like something apart from math? It's up to you, you're a lecturer, you can decide.
It's
like
already written
eating,
now. You're asking him too
your
late.
opinion about food.
No, if you
Yeah,
do
but if you did that.
that.
Yeah, you could put it in like the context.
Oh, yeah, but I just get hungry in the middle of the exam and then I go like,
Oh,
I'm gonna fail this. I'm just gonna leave.
Yeah, I'd rather eat
So,
one, but anyway,
I was trying to do this question,
Yes.
and I'm not sure that I really stated Lagrange's theorem properly.
Okay, how did you state it?
That if H is a subgroup of G, then the order of H must be equal to D when D divides the order of group G. Is that not
Is
the
there anything
full?
wrong with that?
No.
Everybody here?
Yeah, that's
every-
fine. That's fine. We're a bit wordier than I do.
Yeah,
Yeah.
Lagrangian is for if
Yeah, but
there
that's,
is a
that's not the question.
subgroup.
yeah, but that's different. The group, the question asks for a statement of Lagrange's.
Oh, I already did this.
On the order of subgroup. Okay, so what's that?
Well,
I just-
what
Say
Kim
it
just
again.
said, she said, let H be a subgroup of G.
Uh-huh.
Lagrange's theorem states that the order of H must be a number D, where D divides the order of the group G.
Okay, that's all.
That seems fine. That would get 4 marks, I think.
So,
I
Okay,
don't think you
because
can.
that's probably what I'm gonna write.
okay. Because in the book it's really complicated the way that it's done. I think so.
Yeah, they talk about the
Yeah, it
index
talks
and
about-
Talked about cosets, talked about
Yeah.
but it amounts to the same thing.
Okay.
So if H is a subgroup of G, the order of H must divide the order of G. That's all.
That's all. And indeed, if you look at Jan's, so we're going to talk to Jan's solution. Jan has gone minimal. Let H be a subgroup of G, then order of H divides order of G.
See, I wanted to
Or
write
is
that, and I
that
was like,
minimal
nah,
enough
Killian
to
would
get
be-
marks minimal or too minimal?
That would get full marks.
there's
Because,
not really much else you can.
there isn't much to say, and the fact that G is finite is included. If it was just asked about a general group, strictly speaking, in order to make this a valid statement, you'd have to put, well, providing G is finite, this must be, yeah, because we need to know that that's a finite number to talk about divisors of it. But there, it's G is presented as finite. So
Okay.
that would get full marks, yeah. There's nothing wrong with either one, yeah. Personally, I prefer,
I did the words because I knew that you would like the words.
yes, I prefer.
The words aren't very good though.
It's fine, isn't wrong.
They make sense.
The reason I prefer words is very often people can tie themselves in knots trying to reduce everything to symbols and encode everything in symbols.
See, I found something else.
Sometimes it's not so clear. Okay, so part B. So then part B is a step-by-step guide to proving Lagrange's theorem. Yeah.
Uh-huh.
I mean, the harder question would just be prove Lagrange's theorem.
Don't make us do
This
that.
is giving you more guidance, showing you
Yeah, I could.
key things along the way. So state the definition of left and right coset of H in G. And then you see in the introduction to part B, it says let H be a subgroup of a finite group G. So, does everybody know what left and right cosets are?
Yes.
Yeah.
Multiply the sets on the left, respectively the right, by an element little g. So a left coset
I think I did it.
So consider 2 elements of G, G1 and G2. Prove that the left cosets, G1H, G2H. Now, in general, the options for any 2 generic subsets are they're disjoint, they partially overlap, or they're exactly equal. That's the kind of 3 typical configurations of a pair of subsets. Yeah, completely distinct, partially overlap, or identical. For cosets, you don't have the partial overlap. You either have completely disjoint or completely equal. Okay. That's what you're being asked to prove. Now, proving things like this, that one of a collection of things must be true, sometimes that can be a little bit tricky to get a hold of and to get started. So the approach Jan takes is, you see, it might happen that they're disjoint. So what Jan does is he assumes they're not disjoint, and then argues then that so being not disjoint could mean partially overlapping or identically the same. He's going to show that if you assume they're not disjoint, the only option is completely the same.
Why?
That's the way he's structuring the proof. That's how you can prove an or statement like this. Because these are a little bit more tricky to prove directly because you don't have a unique goal you're going towards. It's an or statement between 2 of them. But this is possible. This could be. So what Jan does is he starts off his argument by assuming this is false and then showing that that implies that this is true. And that will prove the disjunction, the or of the 2 statements. They're equal or they're disjunct. We had a similar thing in number theory last year. One clear case that came up was proving Euclid's theorem, that if a prime divided a product AB, prime divided A, or prime divided B. The proof method there was to assume it didn't divide A and show that that implied it had to divide B. It's a similar approach. Okay? So H is your subgroup, G1, G2 is your generic pair of elements. He arms himself with an extra assumption, suppose the intersection is not empty. So the whole mechanics of the proof is in proving that this implies G1H equals G2H. So he's getting himself to this conclusion down here. Okay, so just want to point out the structure of the whole thing. It assumes that they aren't disjoint and show that that proves that G1H is equal to G2H. So how does he do it? Well, once you've realized to structure it like that and you've assumed that the intersection is not empty, a very natural thing to do then is to start referring to one of the elements in the intersection. Yeah. That must be where the thing is going to grow from. So there exists, we can point to at least one element that lives in the intersection. So this element, we know a lot about. We know that this element is in G1H, we know it's in G2H. So because it's in G1H, it can be rendered like this. And because it's in G2H, it can be rendered like that. G1H1, G2H2. Okay. Now what he argues for, so I think he's going to show a subset relationship here.
That's not really cool.
Yeah. So he talks about a G bar. So this is a generic element in G1H.
Yeah, strange.
So if G bar is in G1H, there's an associated element H bar that renders G bar as G1H bar. Okay. So really he's talking about a typical element in the left coset G1H. It looks like this, G1H bar for some H bar. Now notice that when we form this triple product here, H2, H1 inverse, H bar, we get an element in H. So
Just doesn't.
he's really going around the houses here.
Yeah. Why don't I don't get it?
Yes. So read this in right to left.
Yeah.
Start here. So he introduced this G bar that belongs in G1H. For some, okay, this comes straight now. So in reading this, we should start here. G bar, because it's a generic element of G1H, it's equal to G1 times some H bar. Yeah. Introduce H1H inverse. That's introducing the identity in the middle. Yeah. Agreed? Yeah. G1H1 is special. G1H1 we referred to before, it's written as G2H2. So this now becomes G2H2 there. But now looking at the structure of this thing, so this is why his explanation is here. This product, because H is a subgroup, it's closed under products and it contains inverses, this triple product is an element of H. So what you're looking at here is G2 times something from H. What you're looking at here qualifies as an element of the left coset, G2H. Okay. For some reason, we started to write from the right across to the left.
Yeah.
I think it's...
I just don't get.
I just
why that's
don't
needed.
understand why he's done any of that.
Yeah, because you can just go
it's
from
like-
that statement straight to proving it.
Yeah.
Like the G1H1 equals G2H2, you can just multiply by H1 inverse, which we know exists because H is a subgroup, and then you get G1 is in the G2H,
Yes,
which is equivalent to saying there is.
okay, well, equivalent, but he's not calling on that equivalency. So what he's reached here is something slightly stronger than your first step.
But ours is the proof.
The thing that you proved there was that G1 was in H. G1 was in G2H.
Yeah.
Here he's established that anything from G1H is in G2H. So he's established this subset relation. This first one here, that G1H is contained in G2H. And then he argues by symmetry. Okay? By symmetry, you just apply things the other way around. You can prove that G2H is contained in G1H.
Fran's mad because he said if it's weak to argue by equivalence, it's weak to argue by symmetry.
I didn't say it was weak.
No,
what?
Alicia added the word weak. I was just saying you were saying that
No, I used the word stronger,
Stronger.
not to mean that this was better,
No.
but that what he was doing here.
I know, but
was
then he uses
achieving-
symmetry.
Yeah, no, but no, I was just saying because Alicia said you can do the same thing by doing this much quicker argument, but this achieved more than your quick argument that you reeled off quickly there. So I was stronger, not in a value sense, but in a
She was
logical
mad.
sense.
So, can I ask, would our quick version get less
Yeah.
marks?
Okay, so let's examine your quick version.
If we could remember
I
what
haven't given a
letter
judgment
it
on
came
it.
from.
Are you gonna put the same answers in model or your own answer?
Alicia, do you have
I'll put this
anything
on
that makes sense? It's my
the thing,
Yeah.
and if we generate a second one here, I'll put that as well. And I'll also release the printed solutions.
because that's mine, and it makes no sense.
But there's no unique answer to these
As
things,
ever.
yeah?
I just
So
don't like that.
let's
very
complete this
long.
first.
Yeah.
Let's complete this first and then.
Yeah, that's fine.
Okay. So he shows that both is a subset of the other. Okay. At this, having gone to this level of detail going one way, this is legitimate and acceptable to say this, because it really would just be relabeling everything with ones and twos. It'd be exactly the same argument.
Right.
And there's nothing to prejudice G1 over G2. They both play the same role. So whatever G1 can be said to do with relevance to G2, it could equally be said the other way around. That's what he's appealing to there. So now he summarizes, so we have proved that if G1H intersect G2H is not empty, then it must be that they're equal. We may still want to prove that they cannot both happen at the same time.
They can't be equal and
Yeah, so that's,
Yeah.
Jan is being super perceptive here, he's got a very good eye for detail. He's ruling out the possibility that they could be disjoint and also identical, which could happen in the curious case when they were both empty. Because empty sets are disjoint, but at the same time being equal. Trivial. So he says they cannot both happen. Why? Because since H is a group, at least it contains the identity element. So G1 is going to be in G1H. It's also, and if that's equal to G2H, then G1 is in G2H. So the intersection cannot be empty. So they can't both happen at the same time. It can't be that two left cosets are equal and also that the intersection is empty. So he's being extremely careful.
What do you mean? I
Yeah,
don't
he was
get the
just
last bit that you
making a
explained.
comment on 5.
So his main argument
Could be
is that if the intersection is not empty,
Mhm.
that implies G1H is equal to G2.
Okay.
So, well, he says that would get full marks in my mind, because that proves the or
No,
statement.
I'm talking about the last.
Yeah, I know. So what he's ruling out here,
Uh-huh.
he wants to say they cannot both happen. So he's concerned that it could be that the intersection was empty and the two left cosets are equal.
Okay. It could be.
Yeah, but the only way that could possibly happen is if both were the empty set, which can't happen.
So we don't have to put that extra bit in.
No.
The top is. Okay.
Okay, so the crowd says there is an easier,
It's just a bit
more
much for an
straightforward
exam.
way to go about it.
Not necessarily easier, just
Okay.
more.
So how
Yeah.
does it start off in the same way?
Yeah, so once you get to the point where you find that G1H1 equals G2H2, then you can just
Assume it's not empty.
Mhm.
So there exists a G in the intersection. G equal to G1H1, and that's equal to G2H2 for some H1H2. Yeah. So now what do you say?
so G1 is then equal to G2H2 inverse.
So multiply both sides by H1 inverse on the right.
Yeah,
And what do you
which
say about
That
that?
is
product
in
belongs to H.
G2H big H.
So it's H2 H1 inverse.
Which is
Down to
equivalent to
H.
saying that G1 big H is equal to G2 big H by lemma 6.3. Is that the right one?
I think it was certainly in chapter 6.
It is a lemma somewhere in the book. Number to be confirmed. Is it 6.3?
I wrote this part.
Okay. I was just guessing.
This is the proof in the book from 6.4 and Equivalence
Yeah.
which I also wrote for them.
So you say, therefore, so in conclusion, the intersection is empty, or they're the same. Because the intersection not being empty implies they're the same. Okay, what do you think that is in the spirit of the question?
That's the proof in the book, so I'd
Yeah,
be inclined
that's-
to say yes.
That's not what I asked. The book
I know,
isn't-
you're asking if
The book
that
isn't
does
a
it.
response to an exam question.
But it's what we used.
Okay, yeah, no, I'm not, right.
I guess it would depend on
See, the only bit
how
I
much
got
of
stuck
lemma
on-
6.3 is like is 6.3 an essential thing or is it a thing we prove?
Lemma 6.3 is a list of equivalent ways of saying
The
that
same
there
thing.
is,
Equal,
these
yeah.
cosets are equal,
Yeah.
And one of those is by proving that G1 belongs to G2H.
Yeah.
So I would say it isn't the spirit of the question, because if you've learnt those equivalences, then you won't want to use them in the exam.
To be honest, and I love the tone.
Yeah. How did she get the tone onto the paper? That's the question.
So
To
I
be
would
fair,
ask,
if I told Kim's right, I would assume.
Yeah, it was in that tone, yeah.
with this
So what you going to do
paper,
about it?
I always read this slightly.
or just write your notes down on the exam paper you take out, and then email a voice recording to Billy and say, please read throughout marking.
This response should be read in this tone. Okay. So it could be said that the lemma is doing quite a lot of work for you.
Which is very good.
Yeah.
It is. Nice
Um,
work, but then it demonstrates we've learned.
Yeah, indeed. Okay.
And we remember
How
what
would you
we've
mark
learned.
that one? Like how many on the forward back end?
How many marks go for the whole thing?
4 in that question.
Yes.
Yeah.
4 and 3.
Okay, so
And none.
I'm not saying it about this response, but you can imagine a response to an exam question that says, you're asked to prove a thing. You say, oh, this is true because it says so in Theorem 8.2.
Oh, look,
Yeah.
it's not
That wouldn't attract full marks. And there the question is asking you to go through that argument, not to just appeal to that argument, not to just appeal to that result. This is a case somewhere in the middle. But if it was,
I feel like a good 3 out of 4.
yeah, I would almost be saying that upon reflection, if I was impressed by the surrounding elements, I would have a think about it.
So like if you
Oh.
were
What if I stated the lemma? Like,
But if you
very-
stated,
yeah.
but yeah,
Because like if
explicitly.
if I said that and then like, what if then I went on to just show?
indeed, the lemma says something more. It says this is equivalent to.
Yeah.
So I didn't write by lemma 6.3.
Yeah, obviously.
Yeah, I
I
didn't
just
know.
jumped.
But you won't know those numbers.
Yeah, exactly.
No.
So I just jumped
So
from
by a lemma.
by a lemma.
Because you did it from the book.
Surely you can't just write by a lemma.
Well,
Because
by a
then you
lemma
just-
from the course.
You-
Yeah, okay, so
By a
it's-
lemma.
Expect you to remember
By a
arbitrary
lemma.
numbers from this
Yeah,
book.
no,
There is a lemma that exists somewhere.
but I'm not expecting you to remember the numbers, because they're
Yeah.
meaningless. But you can say by a result from the course, as long as you clearly state what the result is. So here it's saying this, so presumably, well, okay, yeah, let's say you would want to emphasize. So by a lemma from the unit, from the course, you could say that, so here's clearly stating the limit. G1, an element of G2H, is equivalent to G1H equals G2H. If you have that written out, full detail, and that slots into your argument here, I'd give it 4 marks.
No.
And just to double check, you are marking that whole.
Yeah, I can always
Give me
phone Jan.
No.
Well,
Yeah,
you're
you
not.
take marks off us.
Well, you can see there's a delicate balance between
Yeah.
doing justice to the question, doing justice to demonstrating your own understanding, which you've convinced me now that clearly stated and well done, this does.
And then there's.
So that's what you're trying to show.
See, 'cause
That's-
it's-
Yeah, if
that's
I'm
what
proving
you're
something, I'm
showing
just going to
It's
try
just
to
a
use the
bit
theorem
hard to
itself
know
in
what
general.
we're allowed
But
to
the-
assume we know, and what we
Yeah.
have to show we know that what
Well,
we
that's
know.
where you have to use your judgment.
Oh, I don't have
I
judgment.
yeah,
That's the problem.
We have a
Killian,
what would Killian want?
But
But you won't tell us.
I mean,
it's not
he
easy
liked
to-
the answer, but it was too long for me.
If
So
it's
I'll
not-
just
I was
risk
gonna
it.
say,
I'll
just
risk dropping a couple marks.
marks. That was like a
You're
full
in the real, this is the real world. You're-
Is
Welcome to the real world. Things are,
Yeah, but it is
Things are
far.
not-
Well,
Yeah,
things are
Everything's
difficult.
fine.
They're unfair.
if it was 8 marks, I'd do Yam's
Yeah,
way.
like
Yeah.
because I just thought for 4 marks,
If it was
Jan's
6
was a
marks, I'd
bit of
probably do
a
Jan.
very
Bit overkill.
long way route to go about it when
But
you can do it.
remember key principles. You're there in the exam, you're demonstrating your understanding of the stuff. You've got a certain amount of time. The timings they're not unkind.
Yeah.
They're could be said to be generous by some.
How many questions we've got to answer?
4.
4 and there's 25 marks. That threw me off. I'm not gonna lie.
So 2 from
Oh,
your
I don't know
part
how
and
to
2.
answer
I'm
24.
used, I'm used to 5
Any
20
four?
marks.
There is no my part, his part. You know.
It's just all,
It's just any 4
Yeah,
questions.
yourself.
6 questions, any 4.
that's also thrown me off. The fact that 25 marks, not 20, because we have to answer
But
4.
remember the principle.
Stress.
The exam is there for you to demonstrate your understanding. There's plenty of time allowed. So,
So 4 questions.
Yeah. okay, here's my final word on it. If you're in an exam situation, that's acceptable to do. Do that, move on, complete the rest of the exam.
And then it
If you've
can
got remaining time,
add more.
stick on a note, say, okay, note, here I'll prove the lemma I used in part C. And
Yeah, I was gonna say,
you
like,
could give a
if
proof of that if you've got time, once you've dealt with everything else. And
That shows
That's-
that I am capable of proving that.
I
that
know.
should have, you know, so you can take that approach. Don't squeeze it in, scribble it in the margin, just have a note at the end. Here I proved the claim used in part C.
It's like over 40 minutes a question.
Is that okay? Siobhan?
No.
I have a side question.
Yes, side question?
Not for that question, no.
Okay. This question, or in
No,
general?
just a general, group theory in general.
dangerous statement.
Not
I like your
pressuring.
question.
When's my
Soon.
list?
Yeah.
When?
He knows
Very
already.
soon.
I wasn't here
Very
yesterday,
soon.
when I can answer them, sorry.
Very soon.
When are we gonna
When
get
is
it?
the-
What's included?
When is the hint list?
Exam solutions
Oh.
and the guidance, yeah.
Oh yeah, I
I
forgot
mean,
your obsession
with,
with that.
yeah, but with,
I mean, I would-
respect, I'm not gonna do anything with it for like the next 2 weeks because of presentations and
Yeah.
posters, but I just wanted to know that
Yeah.
we'll definitely
Yeah.
still
Keep
be
forgetting.
otherwise
When
I'll
did
do
you
that.
get posted?
So I'm looking at the book like there's so much.
Yeah.
A non-group theory related question.
Yeah, okay.
This poster situation, we've been informed through graphics, we might need to have the poster in like with enough time to print.
What's enough time?
to print?
Does it say a
That
week?
was a very
Yeah,
vague.
yeah.
How long is a piece of string? I think what's it?
Have you gone down and asked?
A week.
No, because
A
we
week
don't
is
even know
like-
where it is.
That's what I heard.
Does that
So
mean
you submit your project and then John said you got like the week after your project and you post it and then it should be printed. Like that week.
I mean, I'm just gonna make my poster
The week done the week after you
submit it straight.
Have you done it?
Go down and
Right.
ask.
Consent.
They're in the,
When are you
do
gonna?
you know where they are in the
I
shed?
the
have
weekend.
no idea.
Yeah, no,
I was in there immediately.
Oh, they're in the
The
shed.
other side of the
Project
tower.
Equivalence,
They're in the
right?
shed.
Yeah.
Yeah.
I just said-
Yeah, yeah.
It's a big printer, it's the bit,
But there's no
low,
advantage.
single
if
double
I
story
use
building
my
out in the
extension,
car park.
because you know what I mean?
Yeah, yeah.
I
Beyond
fell
the tower.
behind my revision.
And there's scary stuff in there, and there's big
Very-
sign, big
very
signage pointing
annoying one.
towards it, and then you print city or something, got 3D printer, don't get your poster 3D printer.
Shall we make a 3D
Sorry.
printed poster?
Yes.
Okay,
Yeah, but
Alicia.
if you are late,
Like you done your project.
stand up.
but there are
Right.
commercial
Right.
printers
Right.
around,
I
there
don't
are
think
print
so.
shops,
I'm not
one
sure.
on
Yeah, it's
parallel to,
one too, but
Oxford Road.
Opposite the studio.
yeah, opposite
But then
Street,
if it's
There's one
behind.
called
there's one
I
near
personally
Sandbar,
fell behind
over the
the
other side.
revision.
There's-
Yeah, I don't know if I'm taking it. I'll decide on Friday.
Okay,
Back to group theory.
back to
Yes.
Thank you.
this. Yeah, come on, let's get through this.
So I want to know if I've done this
Part
one.
3, prove that our cosets contain the same number of elements.
Yeah. I finally understand this one. Because I didn't quite get what you two were talking
Have you
about.
had, like so far, students fail their project, like, not fail, I
Well-
mean, like, I don't know.
Steve told me the average in the last couple of years has been like 70 or above.
Yeah, it's in line with other units.
He said they're doing too well. Those are his words, we're doing
Anyway,
too well.
let's get through this, okay? So the proving every coset has the same number of elements.
I don't like that. Lambda is injected as I proved in question 2, part F.
Hang on.
I don't remember question 2.
Okay, so you consider the,
How can you
Isn't that
not
the
prove
next
it?
question?
Oh, no, this is not how I've done it.
no, this is part 3, proving that all
cosets
cosets have the same number of
are
elements.
then the same number of elements.
Why is it G
G1
to
and
G?
G2 belong to G, if I remember.
Yeah, what should we do? Because
Should not be like H to the coset.
Yeah, so I think he's showing here that he's setting up a bijection between any left coset G1H and any other left coset G2H,
Oh, I don't like
right? which is one way of doing it.
So any bijection.
Now he's constructing a
what
specific
we do.
bijection from a coset G1H to the coset G2H. Because it's a bijection, they have the same number of elements.
Okay, yeah.
And then he says by symmetry, it will also apply to right cosets as well. Just repeat the same argument on the other
I
side.
forgot to add a bit
And
of
applies
right
there,
concepts.
Oh, yeah.
Oh, shit, yeah. I didn't know
A simpler
that. Symmetry.
way to do
I feel the way
this
too.
is use H as a reference coset and show that every coset is the same size as H. And by extension then, by transitivity of equality, they all have the same size as each other.
It's easier.
Yeah.
And
So
you
I think
prove this.
I think this is more straightforward.
Okay.
Okay. So the map lambda g of x, which is equal to left multiplication by g, is a bijection. Is a bijection from H to the left coset GH. Okay. You can appeal. Okay, so he's appealed to an earlier argument. You can say it's injective. So G1, GH1 equal GH2 implies H1 equals H2, so it's injective. So this is the proof of bijective. 2, for surjectivity, yeah, clearly.
So, see, this is the issue I have with subjectivity. It's just basically
It's
going,
just kind of
look at it.
Yeah.
Like,
Well, then, yeah, it's clearly
if I write in my exam subjectivity, just look at it,
surjective.
Killian.
Clearly surjective as H maps to GH.
What does mine say? What will G belong to G?
So since there's a bijection, therefore, cardinality of G1H is equal to the cardinality of H. Okay? And so all cosets, all left cosets, all left cosets have the same number of elements. And I think this is a better way to do it. Namely, this number of elements is the number of things in H. By symmetry, using the map mu, which is again is referenced by G, but this time we multiply on the right by G. Using that map mu, all right cosets contain H elements as well. That seems a lot more direct. Jan, so what Jan is doing is he's constructing the bijection from any particular left coset to any named left coset to any other named left coset. Whereas we just talk about the bijection from H to any left coset.
Would it be enough to just write it's clearly like bijective basically?
Well,
Like, you'd have to do a full proof on it. Because I haven't anyway.
you just said
Means
that
it.
this map is bijective.
No, I've done a proof of it.
That amounts to this.
Yeah.
Well, I would like to see I would like to see you explaining that you understand why it's a bijection.
Like, I've proved that it's injective, it's the surjective.
Yeah,
I just never know how to prove that.
There isn't. It just kind of. It is. I agree with you. It is obviously true. H is the element that maps to GH. I mean, that's. You're just restating the definition. X maps to GX.
Yeah.
Okay. Then show
Is
how
it
part.
mainly, you're right.
Mainly, yes. So that's a version of.
So, is origin.
Okay, everybody got 5 minutes left, correct? Stuff is over.
We're chatting too much.
Yeah.
We're talking about running.
Right.
Yeah.
Food and running.
Food. Printing.
Show how parts 2 and 3 can be used to prove Lagrange's theorem. So some version of the overall argument. The number of left cosets of H, let n be the number of left cosets. By 2, the left cosets form a partition of G. You should also note that any element little g is living in the left coset generated by itself. So therefore, the union of all the cosets is indeed all of G. By 3, the size of each coset is the order of H. Hence, the number of things in G is n times the number of things in H. N is the number of left cosets, the number of cells in the partition. Therefore, you're looking at a statement that says H divides G. Okay? So there's not much required, you just have to link together the 2 parts to mention the partition. Okay, part C is something. I think this was an exercise. So suppose H and K are subgroups of the group G. We define a relation tilde. G1 is related to G2 through tilde if you can find little h and k such that HG1K is equal to G2. It's a kind of a generalization of conjugation, you could say. State what an equivalence relation is and prove that it's an equivalence relation.
I don't think I know how to define an equivalence relation.
Okay, well, here it is. Equivalence relations are relations that act like equality. They're the relations that take a domain of elements and partition them into equivalence classes. They gather together all elements that are all equivalent to each other, all related to each other. So a relation is an equivalence if it is, so this is how we technically define it, it's reflexive, symmetric, and transitive. Reflexive says everything is related to itself. Symmetric says if 1 is related to 2, then 2 is related to 1. It's the original statement refers to an ordered relation. Yeah, the left thing is related to the right thing if there exists the little h and k. Okay. It doesn't necessarily say that it automatically follows that G2 is related to G1, so we'll have to prove that. And finally, transitivity. If 1 is related to 2 and 2 is related to 3, it necessarily follows that 1 is related to 3. So the relationship travels through intermediates. Now, we're proving these 3 properties for this relation. H and K are subgroups. So the technical devices, the technical justifications we need are probably always just going to be referencing various subgroup properties of H and K. Yeah, that's what you've got at your disposal. So to be reflexive, how can you prove that G is related to G? Well, to prove that G is related to G, you have to put something from H on the left of G, something from K on the right of G, and have the whole triple product equal to G. So the thing that'll do it for you is E. E is present in both because both are subgroups. So EGE is equal to G, so that means G is related to itself, according to the rule. The rule is this is related to that. If you can find something from H and something from K to put either side of this, that makes it equal to that. Yeah, so here it is E and E. Okay. To say it's symmetric, well, to prove symmetry, you assume that 1 is related to 2. So if we assume 1 is related to 2, that means we can call upon the existence of a H and K that do the job. Yeah. But then you just invert this relationship. Yeah. H1, G2, H1 inverse, G2, K1 inverse. You substitute what G2 is, the inverses cancel, and you get G1. So there is something from H, there is something from K that will kind of conjugate G2 to give you G1. Yeah? So this proves that if 1 is related to 2, then 2 is related to 1. And you're making use of the fact that subgroups contain inverses. Yeah. Maybe mentioning that there might be a good addition to that. Maybe mention.
He has kind of put belongs H above the inverse bits, where he's written H
Yes,
inverse.
yeah, okay,
He ha-
yeah.
he's
So
just-
he's squeezed in here.
Yeah.
This is relying on the fact that H and K are subgroups. Finally, transitivity. Transitivity is going to rely on the closure condition. It's to do with combining things, kind of. So you assume G1 is related to 2. You assume 2 is related to 3. That means you're assuming there exist certain pairs of elements, H and K. So H1, K1 are the ones that conjugate. Okay, it's not conjugation. Okay. H1 and K1 are the ones that do the thing to G1 to turn it into G2. H2 and K2 are the things that do the thing to G2 to turn it into G3. We're looking for left and right elements to multiply G1 by to get G3. So skip over the intermediate. I mean, you stare at it, you figure it out, you substitute around. I mean, what we do is we substitute for G2 in here. So if you replace G2 with this, you see it's H2, H1, K1, K2.
That kind of does it backwards.
H2, H1 is in H, K1, K2 is in K.
Like, why does he does everything backwards?
That's fair. That's more or less just what I said.
Well,
Replace.
yeah, it's just like the opposite way I would think of it myself. No.
Yeah, I would start with G3 is equal to this by assumption. G2 can be replaced by this by substitution, and then associativity to just kind of emphasize the products either side of G3.
Yeah.
So therefore, G1 is equal to G3, and you're appealing to the closure condition of H and K. So therefore, all three properties are true for tilde, so tilde is an equivalence relation. So that would get full marks. I'd maybe like to see some comment here, just to emphasize we're using the subgroup, the fact that H and K are subgroups is used in several places. You don't literally have to write it in every single place. These comments are enough, but maybe just a statement at the beginning. Each step is justified by the subgroup properties of H and K. And then you talk about E is in H, fine, B is in K, fine, H1 inverse is in H, K1 inverse is in K, fine. Okay? Okay, so I'll put a scan of that together with the alternative versions we produced for a couple of parts there. So Thursday, number 4. Fine deal with 4, 5, and 6.
4, 5, and 6?
No, not that. Okay, thanks for your attention.
Guys, we've really got like 1 and 4 week of lectures. Like, no, but like ever.
Well,
Not ever.
not everyone.
Yeah, no, together though.